say for example some agglomeration and some like mixing materials. So based on that, so first we'll have a Stokes law. As you know that the Stokes law is useful when we are talking about a particle that is flowing in a stream, in a fluid stream, right? So the settling velocity, or the way it is taking to settle, will be helpful in determining the particle size distribution, right? So in that context we'll be doing some numerical on Stokes law. It says that the particle of A of diameter 10 microns, so you're given a particle A which is having a diameter 10 microns, right? So you have 10 micron diameter, settles in an oil of specific gravity zero point 0.9 and viscosity 10 poise. So you are giving some characteristics for the oil, like for the fluid, which is having a specific gravity zero point 0.9, as we discussed earlier, that specific gravity is defined in context with the like in context with water. If it is specific gravity, it will be in context to relative or to that of water, or specific density, it will be relative to what it is for the water. So this is viscosity and the properties of the oil under Stokes law. A particle B with diameter 20 microns settling in the same oil will have a settling velocity. So you have to calculate what will be the settling velocity for a particle which is settling with a higher diameter. So you are having two diameter particles. One is 10 micrometer and one another is 20 microns. So based on Stokes law, you have a relation which says that the terminal velocity, it is equal to some function of diameter square, some function of viscosity of the medium, and something like the density of the fluids, right? Density of the fluid minus density of the material, something like that. But because we are talking about the same oil, so the density will be constant here. The density also, because the density of the particles is not changing, the diameters are only changing. So this density of the particle will also remain same. The viscosity will remain same. So we'll be only discussing what will be its effect on the diameter. So you have to calculate the terminal velocity effect. So because we have to calculate a settling velocity. So we can write V1, which will be the settling velocity for case 1, and V2, which will be the settling velocity for case 2. So that will be equal to the diameter in case 1, square of that, and diameter of the case second, square of that. So now you can calculate what is the settling velocity relation between the two, easily putting your diameters. So can you tell me what is the relation by putting of the values? So this will be 10 by 20. Right? So we have V1 or V2. V2 is equal to 4 times V1. What does it mean? It means if you have a particle of a higher diameter, the terminal velocity will increase, right? That means if you had a particle, for example, 10 micrometer, if it was moving with the speed, velocity, say 1 meter per second, so you have a terminal velocity now 4 meter per second, right? For a particle of diameter which is 20 microns. So that means with increase in the diameter, the terminal velocity also increases. So this is what we were trying to do. This was a relationship between the settling velocities of the two particles. So now we can say that the settling velocity of the particle 2 is 4 times the settling velocity of particle 1. Is it clear? Any questions on this? Then we will move to the next.
No, ma'am, it's fine.
Okay.
It's fine.
So now we have another question. This says find the angle of repose if the diameter of the pile, sorry, it says that find the angle of repose if the diameter of the pile is 2.7 centimeter and the height of the pile is fixed at 1 centimeter, right? So what you are trying to make sure, you are putting your material through a, for example, a funnel, and then you are seeing how the material is flowing out of that funnel and how it is forming a heap. So it will be mostly forming a heap of particles like this whenever you pour your material through this. So this is one of the techniques that helps you to determine the flowability of your powder, right? If it is flowing very well, so this angle of repose will change. This angle of repose and your flowability will have a great difference, like it will have a direct relationship. So you can say that this angle of repose is a function of your flowability. It will help you to estimate how your material is flowing, right? So, for example, mostly this test is largely done in, I discussed this in the last class. This test is largely done in also in places where we are testing sand, slits, clays, like similar, like the civil engineering background. They will understand it because they usually let the sand or slit or the material they are concerned with, the construction material, they will let it fall, and they will let it fall on a flat surface and let the pile of your material be formed, the heap will be formed. So then they will calculate from this heap the angle of repose. So how is this angle of repose calculated? We know that it will form a heap like this. It will be somewhat a triangle. So they will calculate this angle theta. This angle of theta will be calculated. So this will be related to your height. So you know that angle of repose is equal to tan of theta is equal to the height of your pile which you have formed and the radius of your pile, right? H by R. So this is your relationship between the two. So mostly how will you calculate this angle of repose? It's very easy that you take a funnel, you let your material or powder pass through this funnel, and you have a flat sheet of paper or something at the bottom. So once it is falling, it will form a pile. So you can know the height of from the pile. You know how what is the distance from this point to this point. That will give you height, and based on how much coverage it has covered, maybe if you draw a circle, you will understand that what is the coverage. So it will have some diameter, and then you can calculate the radius. So that will help you estimate this R. So this is an experimentally you can calculate H and R, and based on those you can calculate the angle of repose. So in this question you are asked to calculate angle of repose if the diameter of the pile is 2.7. So you are given 2R, that is 2.7 centimeter, and the height of the pile is, that is H, that is given as 1. So you just have to calculate the angle of repose. So that will be 1 by 2.7 divided by 2. So that will be 2 by 2.7. So you can calculate the theta from here. That will be tan inverse of 2 by 2.7. You can calculate it and let me know what will be the answer for this. Calculate it and tell me what is the answer. I think the angle will be something about 36 degrees. 36 degree. So there is now one question, that what will help you to determine the if it is a good angle of repose or a bad angle of repose, which will give you an idea about the um, flowability of your powder. Say for example, now if you have this kind of a pile, it is having a theta of, say for example, this 30. Now you have a pile that is having an angle which is greater than 30. So this will be something like this, right? So now it has an angle of 60, right? And or you have an angle which is greater than these two. First, if we discuss these two, you will understand that if it is having an angle of 30 degrees, that means the angle of repose is less. But that angle of repose is less because the powder that you are making it fall on this pile, it is flowing easily downwards and it is making a bigger circle, right? So it is having a good flowability because angle of repose is less. But if you have angle of repose is large, that means what happens that the particles are getting accumulated on the pile and they're not easily flowing downwards. So the flowability of the particles is bad. So you can say based on the angle of repose if your flowability of the particles, powder particles, is good or bad. Is it clear? So
Yeah, ma'am.
based on the angle of repose, you can calculate the flowability. Okay. So then moving on, now we have questions related to some MCQs. So for first question says, for a perfectly mixed random powder, the homogeneity index is, what is the homogeneity index? Is it 1, 0, 0.5 or infinity? uh, Basically you know that when you have powders like we also discussed this last time, if you have a mixture of powder, if you have a big powder, small powders, or there is a difference in the powders based on their density, there is a difference in the powders based on their shape, if there is a difference between the powders based on their size, then these particles will try to segregate or they try to be divided based on these characteristics. For example, if you have a density based difference in the particles, you have a heavier powder and a lighter powder, that will tend to get segregated into two streams. Similarly, based on size, they will be segregated. So, in order to prevent the segregation in the powder, because we want to have a homogeneous mixture of the powder before we go for processing or formation of the powder compacts. So for that, we need to homogenize the mixture. So for homogenizing the mixture, we have an index that determines our homogeneity, and that homogeneity index is varying from 0 to 1. So when it varies from 0 to 1, what you mean by 0 to 1 means that at 1 the mixture is completely homogeneous, and at 0 the mixture is random. It has no homogeneity in it. It is having some segregations in them. So for a perfectly mixed random mixture, the homogeneity index would be 1. So this is the right answer. Right. Now, next question says that we have deagglomeration. Deagglomeration is crucial for finer particles, coarser particles, both A and B, and none of the above. Can you answer this? Which of the following you think it has deagglomeration is crucial?
A, minor party.
It is crucial for finer particles. Why? Because also based on your based on your calculations, you might have seen that if you have a very small particles, these particles have a high surface energy, and because of the electrostatic forces, they get attracted to one another, and these attractions result in agglomerations. Mostly coarser particles do not agglomerate, but finer particles agglomerate. It is mostly because there are certain electrostatic forces or electronic attractions between the two particles because of high surface energies. They tend to agglomerate together, and thus deagglomeration is crucial for the finer particles. Then we have another question which says that in an experiment, alumina powders are mixed with 5% PVA binder, right? PVA binder is a polyvinyl alcohol, so this is mostly used as a binder to bind the powders together. It is also used for pellet making when you want to make pellets of certain materials, so you can use PVA as a binder. So the binder liquid pulls the solid particles with a force proportional to. So it is saying that if you have a particle like alumina like this, you have another particle of alumina, and in between this there is a PVA binder. This PVA binder forms liquid bridges between the two particles, and that is why they are getting binded together. Now it is saying that the binder liquid pulls the solid particles with a force. What is the relation between the force? So this force will be related to the solid liquid surface energy. The solid liquid surface energy, solid vapor surface energy, liquid vapor surface energy, or particle diameter? Can you answer this? Can you answer what is the it is based on? It is related to surface energy, but what kind of a surface energy? And particle diameter, obviously based on if you have a particle diameter, it will be influencing by the particle diameter. So the force will be proportional to the particle diameter, because if it is a larger particle, the forces will be less, but if it is a smaller particle, the forces will be large for agglomeration. So that is why when you're talking about finer particle deagglomeration, you always know that the force that is acting for a particle of diameter, which is small diameter, will always be high. So for a smaller particle, the force will be a force of agglomeration will be very high. That is why it will be a function of particle diameter. But what out of these is the right answer? Solid liquid, solid vapor, or liquid vapor? Basically, if you do a force balance in between this powder, like between the binder and the uh, solid interface, there are various interfaces. First, solid liquid interface is between the binder and the aluminum powder. Then we have solid vapor interface, that is between this solid and air material. This is which is the outside of this. So we always have a three interfaces. If you know there is this surface, and if there is a particle of water on it, which you might have read in your contact angles formation, this is a surface and there is a water molecule on it, and this is an air. So we have two surfaces. We have solid, liquid. So for example, this is liquid and this is air, which is the vapor phase. So we can write it vapor phase. So between the vapor and the liquid phase, there is a one interface, and this will be based on surface energy will be the vapor and liquid, between the vapor and the liquid. The surface energy in this surface, where we have two surfaces in contact, the vapor and the solid, so the surface energy will be gamma Vs. Then we have another interface, which is this solid liquid interface. So that will be here. So this solid liquid interface will be here. So basically we have three interfaces, but in case of when you are talking about binder and forces that are proportional to it, you might have seen that there is an equation that says the strength of this binding is directly proportional to your say this is your strength. This is directly proportional to your liquid vapor interface and your diameter of the particle, and there are some other factors like porosity and everything, but this is the surface interface between the liquid and the vapor. So the right answer is liquid vapor surface energy and particle diameter are the influencing factors when you're talking about mixing of the powders or binding of the powders. The binding strength will be determined by the liquid vapor interface and the particle diameter. Then we have another that says pick a process suitable to prepare a green compact for a component that is expected at a production rate more than 10,000 or 1 lakh units per year. So first thing that is important is that we are talking about green compact. What is a green compact? The green compact is any compact that has yet to go to sintering. Anything that is before the sintering process is called as green. For example, we have green density, we also have green compact that has not undergone any at like any preparation method before sintering. We call it as a green compact. So for that, we have based on our production units, based on how much can be produced per year, we have different categories of products that can be produced. So based on this large amount of per year, we need a technique that will be sustainable. So for this large time sustaining technique, which of the techniques will be suitable? So So you have to tell, is it for fabrication, slurry casting, cold isostatic pressing, tape casting. Preform is mostly done when you have very less production rates. Very less production rates. Slurry is for moderate production rates. Cold isostatic is also for moderate because these are used for 2D manufacturing of the particles or powders. And then we have tape casting. This tape casting is used for production of large amounts of uh, powders, compacts. So tape casting is the right option because these are methods for compaction. So now we have another compaction that says to get a 3D compact, which powder shaping technique will be employed? Tape casting, extrusion, slurry casting, or injection molding? Any answer for that?
Injection molding, I think.
Yes, one of the options is injection molding, but also slurry casting. Though they have different production rates, injection molding and slurry casting both are used for 3D compacting. Uh, Now, the next question says the temperature needed to debind the compact completely is 600, 200, 100, 1000 degrees Celsius. So, if you have bounded the compact, now you completely want to debind it. So, what is the temperature that should be utilized? Because what you are trying to do, you are basically adding some binding agents, right, in your powder material. So, for example, you have a powder of copper, so it is a metal, and then you are adding a binding material which is something like wax, it is or it is cellulose, or sometimes it is zinc stearate. So these are all organic molecules that are added. Like you said, you checked, we had PVA. This is also a organic molecule. So you are adding some organic compounds as a binder for binding of the powders. So if you want to debind the powder, if you want to remove this binder, so what is the temperature that should be operated? If you can see from these temperature ranges, what is the temperature that we should utilize? Any answer?
Either 200 or 100 lower temperatures.
Well, see, wow, at 100 we can only remove the moisture basically. Nothing else will be removed. The moisture or the volatile, if there is any compound, that will be removed. At 200 is also a low temperature. If we have to go about 600 degrees Celsius to debind the compound. Basically, how we are trying to see, for example, if you have a PVA molecule, what you are trying to see, there is one technique that is called as TGA, thermogravimetric analysis, right? In thermogrametric analysis, you will find what is the percentage time. For example, if you have a temperature on one axis and you have a weight percentage which is lost, weight percentage or remaining, we can say, right? So you take a small amount of a powder or small amount of your material and you put it in a aluminum like pan. You heat the material at a constant heating rate. After heating the material goes through various changes, mass losses because of evaporation, because of reactions, oxidation, reduction reactions. There is a mass change observed in the material. So that change in the mass is reported in the thermogravimetric analysis. So based on the temperature, we have a curve of weight remaining. So for example, if we have something like this. So what we are saying that with increase in the temperature, the weight that is remained is decreasing, obviously, because the material is melting, evaporating, it is getting removed. So based on TGA, so for example, if you want to find the TGA for like for a PVA material, we will go subject it to TGA and we will find a temperature at which the material will be evaporated, right? So, for example, we have a temperature like 600 degrees Celsius. We found that the maximum of the mass has been lost for this PVA. So, we will choose the 600 degrees Celsius. So, basically, for all organic substances, when you are increasing the temperature, they degrade. They try to decompose into smaller polymeric chains, and as they decompose, there is a decrease in the weight. So this will help with the help of a TGA analysis. You can identify what is the appropriate time required, sorry, temperature required for their decomposition or for their removal of the binders. So basically, because these are organic molecules, the temperature that is utilized is about 600 degrees Celsius. So also while you are debinding the material, you should also see if there is any change here to your main powder material size. For example, here we are talking about copper. But if it is some other material, is there any phase change in the material? Is there any change in the morphology? Or if there is any effect that is happening to this material, so we need to check also that. So this debinding is basically related to your binders which are used, and these binders are basically organic materials, and so the temperature of their removal is about 600 degrees Celsius. Okay, so now we have another question that says typical lubricant used during powder compaction includes zinc stearate, wax, cellulose based additives, or all of the above. Can you answer this? These are also lubricants, or as we were saying, debinders. So can you tell what are the typical lubricants used in the powder compaction? Is it A, B, C, or D?
Zinc stearate, ma'am. First.
Uh, the answer is actually all of the above. So all of these are used as lubricants because, as you know, the lubricant is basically added because we do not want any friction between the dye walls and the material. So for example, this is a dye wall and you have put your powders in it, and at the walls there is some friction between the particles and the dye wall. So we do not want that friction at the walls. So basically for that purpose the lubricants are added during the compaction process to minimize the interparticle abrasion or interparticle wear during the compaction process. So all of these are able to be used as a compacting material. So next question is the purpose of.
Question, ma'am.
Mhm.
Yeah. So lubricant and binder, two things are there. Now, uh, if if these are also used as lubricant, all of the above, then what is used as binder?
Binders
Because
are
what
also binders are such as, like I told you, we have one of the binder is this PVA also. Then also, for example, if you know, it depends on what kind of a process you are doing. In processes like, if you know, pellet making or iron making, there is one binder that is used that is known as bentonite. So bentonite as a clay is, bentonite clay. That bentonite is used as a binder in case of like iron making and pellet making processing. That is also one of the methods of compaction or pelletizing. So that is bentonite. We have polyvinyl alcohol as a binder. We have also boric acid is used in some cases as a binder in some compacts. So based on what kind of a powder we are taking, based on that the binders will be utilized. So they are, some of the binders are like this bentonite or PVA, so you can use these as binders.
wax is also used as binder,
Wax is
right, ma'am?
mostly used as a lubricant only because see, wax is mostly just used to avoid the friction between the materials. That will be mostly used as a lubricant, but not for a binder, because for binder you need to have a like a force of attraction or force between formation of a liquid bridges or formation of van der Waals forces between the two particles. So wax will not be a good choice because it will just reduce the friction between the two particles, but it will not be able to join them through any physical forces. So for that, wax I don't think so is used as a lubricant. But yeah, wax cannot be used as a like binder. So the properties of lubricant and binder you need to understand. The lubricant is basically just to avoid the interparticle frictions or in particle friction between the particle and the wall. But for binder, we need to have some physical attractions, physical liquid bridges formed based on van der Waals forces. So once those will be formed, then the particle will bind together, and then it will form a compact, or it will form a pellet. So based on
Yeah,
that,
so
yeah.
all these three are zinc stearate, wax, cellulose based additives. all are lubricants only. None of them is used as binder in any case.
No, no, they are lubricants.
Okay, they don't play role of binding or binder also. All are purely lubricants.
Yeah, yeah, they're purely lubricants.
Yeah. Okay. Yeah.
Okay, so now we have another question that says the purpose of coating a material over the powder is to avoid sintering process, to for preventing undesirable chemical reactions, for alloying, for lubrication, to be used as a binder, all of the above. So for example, we were saying that we are trying to coat a material over the powder. Like we had a powder and we are trying to coat it with something. So what could be the possible reasons that we are trying to coat it with some material, say for example? Is it to avoid the sintering process? Is it for preventing undesirable chemical reactions? For alloying? For lubrication? To be used as a binder? All of the above. So basically we know that for lubrication or for binding there will always be some coating on the material. So these are true for a material that is being covered with another material, for powder that is covered with a material. So lubrication binding is right. For alloying also we try to use certain alloys and we try to like spray them on the particles to alloy them once they go for compaction and sintering process. Say for example, if you have a cobalt particle, you will have some particles coated on it with some another alloy powder with which you want to form an alloy. So you can have a have this configuration for alloying purpose also, for avoiding undesirable reactions also, because we do not, if you want that the particle should not be oxidized or the particle should not react with the atmospheric nitrogen oxygen, then we can coat it with some material to prevent its reaction, because they will prevent its from reacting with the environment. Also, for example, if you have a material that reacts with some medium, then we try to coat it with the binder and it will not react with the liquid medium for some actions. So for example, we do this process in the hydrometallurgy, where we have, so for example, if you have a powder of copper, just as a hypothetical example, where you have a powder of copper and you are dissolving it in a or using in an aqueous medium which is acidic, so it will tend to react with the aqueous medium and it will form copper ions. But you do not want that to happen. So for that you can coat it with certain polymer, for example, for any polymeric material. So that polymeric material will not allow the copper inside it to react with the aqueous medium, and as such your undesirable chemical reactions will be prevented. This is also right, and also to avoid sintering process, because sometimes we tend to mechanically alloy the material. So during mechanical alloying, we will can tend to have a coating of one material on the other, and that will prevent your going for a high temperature processing. So this is a coating process are required for all of the above. Then we have another question that says that higher green density is favored by. So as I said, the green is something that is before any sintering process. So which of the particles will you expect to have a higher green density? Is it higher hardness or lower hardness? So if you have two particles, one particle which is having a very high hardness and you are trying to compact it, and you have another particle which is having a low hardness and you are trying to compact it. So which will have a higher green density? Basically, green density is like how it is more of a theoretical density and also their density before you are going for a sintering process. So you are just saying that if you have a hard, for example, hardened balls, and you are trying to compact them, they will have a tendency to abrade one another because of their hardness. They will try to get abraded with one another, and the density obtained in such cases will not be that high. But if the hardness between the particles is less, there will be less interparticular friction, interparticle reactions will be less, and as such, the density of the material will be high. So we can say that the higher hardness can be achieved if we have if we have a lower hardness of the material or the powder, the higher green density will be achieved. So based on your particle characteristics also, we have to understand the particle shape, particle morphology, or particle size. We have to also identify the particle characteristics in terms of its hardness, roughness, or smooth surfaces, how the surfaces behave, and all of this will influence your compactability and flowability in a compaction process or their density subsequently. So, example, you're trying to have uh, a successful molding means that you're trying to compact the material. So, during compaction, what are the parameters that should be favorable for the mold? Is it high pressure, low viscosity, high viscosity? You can answer this. What do you think is the right parameters for good compaction? The parameter which is needed for successful molding. So if you have a high pressure, it will be favorable for formation of the mold, right? Because high pressure will help in higher compaction, higher filling of the voids between the particles, and therefore there will be less porosity, and overall we'll have a successful mold form. So high pressure is one of the options. Then we have another option also on low viscosity, because if you have a highly viscous fluid material, it will not flow easily in the mold. So that will be difficult to compact. But if you have a low viscous material, that will easily flow through the mold and it will be a uniform mixture of the powders. So low viscosity and high pressure are the favorable parameters for having a good or successful molding, right? Now the next question is, work hardening is prominent in small particles or larger particles? This work hardening happens during compaction when you have mostly metallic uh, powders. These metallic powders under compaction tend to get work because of their inherent property, because there are metals, they have an inherent property to deform, they have a plastic deformation, so they will tend to work harden. So during work hardening, which of it is right? Work hardening will be prominent in small particles or in larger particles?
Is it small particle, ma'am? Because volume is less and
Right. Right. The work hardening of the smaller particles will be more, as you might have also read, and there is one theory that is related in to mechanical metallurgy that says, that is a Griffith theory that says that if you have, there is some relationship between the particle diameter and some stresses. So it says that if you have a very small crack size, that will propagate at a faster rate than if you have a larger crack, right? Because the stresses on the point are very large. For example, if you have a point and the stresses that are acting on this point are very large, but if you have a larger crack, the stresses are distributed, so the stress is not that large. So always when you have a smaller particle, because of the higher interparticular higher surface energies, higher interparticular friction is possible. Higher interparticle friction will result in larger deformations, and those deformations will result in work hardening of the material. So always small particles will be more work hardened as compared to large particles. Then we have another question that says that at high compaction pressures, the H by D ratio increases, decreases, remains constant, or insufficient data. So this is related to your pressure. So you have a equation that's related to your how much compaction pressure you are giving, and what is the effect on its H by D ratio, right? So what is the H by D ratio? H by D ratio is a characteristic of your particle. It says that what is, for example, if you have a particle, it is a sphere, this will have a different H by D ratio, or if you have a oval, that will have a different H by D ratio. If you have a cylinder, you have a different H by D ratio. It's based on particle morphologies. These will change, and the compaction pressure will also be affected. So you have to say, if you have a high compaction pressure, the H by D ratio will increase, decrease, or remain insufficient. Basically, there is a relationship between the particle. If you have seen that there is a part pressure that is related to pressure at ideal conditions, and it is there is some exponential term that is something like this 4 mu. This x by d is actually the h by d factor. This you might have covered this in your classes. So if you have a lower pressure, if you have a higher ARD, you will always have a lower pressure. So here, because we have a high compaction pressure, the H by D ratio will decrease. Just based on your equation, you can conclude this, right? This is also practically possible if you imagine a die that is compacting. The H by D of your particle will decrease. Why? Because it is trying to compress the particles, and overall the H by D ratio will tend to decrease as the particle is being compressed. So just visualizing based on your visualization and based on your equation, the high compaction pressure will decrease your H by D ratio. It will tend to, for example, if it is a elongated particle, as you impart compaction forces, it will try to compress. From a cylinder it will be decreased, it may form a cube. From a cube it may compress again, it may become a rectangle. So you can have a different high H by D ratio will decrease. So the next question is, during compaction, the pressure at top of the compact is equal to the pressure at the bottom of the compact, because we are trying to compact, say for example, this material. There are two things: the pressure that is on the compact and the particle pressure that is uh, just at the bottom of the compact. So is it same? Is the pressure at the top, which is PT for example, and the pressure at the bottom, which is PB, same, or it is not equal to each other, or the pressure distribution is unaffected during compaction? None of the above. So can you tell what is the right answer? Can you tell what is the right answer for this? The pressure at the top or the pressure at the bottom, will it be same or different?
Is it same, ma'am? Only at the center it changes.
Well, no, the pressure at the bottom and the top of the compact will not be same. Why? Because we know that these are the particles that are going some deformation. So, for example, if you are giving a pressure of PT at the top, the pressure at the bottom will be less than that, because some of the pressure is being distributed and it is being utilized in interparticular frictions, interparticular work hardening, or any other processing that happens in the inside of the material. So the pressure will always be less. The pressure at the bottom will be less than the pressure at the top. What you are giving at the top will not be same at the bottom, because the material is going through some changes during the like during pressing or during giving that pressure for compaction. So the right answer is that the pressure at the top and the pressure at the bottom is not same. Okay.
Yeah,
Uh,
but if it is a thinner compact, the difference might be less, no?
The difference might be, yes, the difference between the particles will be less, but it depends on lot more factors. It depends what is your material, what kind of a material you have, what is their properties, how are they aligned, are their shapes perfectly filling, are they, if they are perfectly prepared, they will have a good like filling capacity, so they will fill quickly, and there will be no, the pressure will be equal. But if there is orientation of the particles is different, if the edges of the particles are angular, say for example, so there will be friction between the particles, so that will not allow the pressure to be same. So it depends on multiple factors, so it cannot be generalized that how much difference will be the between the pressures. It will depend on your material. So now the next question is, during compaction, strain hardening occurs in aluminum, gold, tungsten, Al2O3. which of the following do you expect the strain hardening to occur? You know that when you're going for compaction, there are different stages. There is one stage that says that there is a rearrangement of the particles happening. There is another stage that says that once the particles have rearranged, they are now trying to deform. There is a deformation stage in the particles, and in third stage there is either strain hardening or there is a fragmentation based on what kind of a material it is. If it is a metal, it will strain harden, but if it is a brittle material, it will fragment, it will break into pieces. So there will be fragmentation. So based on what kind of a material you have. So these are the stages of your compaction process. So you are asked that the strain hardening will occur in which of the following: the aluminum, gold, tungsten, Al2O3. In which of the following do you expect strain hardening to occur?
Aluminum and gold.
Uh, Aluminium, right? Because it is a metal, so you expect strain hardening. Also in gold, you expect the tungsten Al2 will fragment because of their properties of being ductile, or sorry, being brittle. Okay. Now, next question is mention the phenomenon that occurs in maximum compression pressures. This is what I was talking about. That there are different stages of uh, that occur during compaction process. So this is one that says that if you have a maximum compression pressure, because you are changing the pressure and there are changes that are happening inside the material. So you might have seen some graph like this, which says that as you this is something like this. This is the compression pressure, and this is, say for example, fractional change in density or basically density. You can say so based on when you are starting here, you are at the apparent density. When you are starting before the compaction, the density is known as apparent density because it is not compacted yet. So there will be apparent density here. Once the material is being compressed, there will be some rearrangement of the particles that will be taking place, and it will reach a stage where there will be some deformations, and after that a maximum deformation has taken place, right? So it will try to saturate. So there is, if you are increasing the compression pressure, there is no significant difference in the density because you have reached the limit of your compression pressure, right? These are various stages that take. This is stage 1, this is stage 2, this is stage 3. So based on at what type or at what compression pressure you are, you can have a different stages. So we have the arrangement of particles, homogeneous deformation, localized deformation, and then bulk compression. So what do you expect when you have a maximum compression pressure? When you are somewhere in stage 3, what is the phenomenon? What is the process that you expect to occur in the compression process? Is it A, B, C, or D?
I think D, bulk compression.
Alright, at maximum compression pressure, there will be a bulk compression. Initially, what happens? The rearrangement of particles takes place. Then there is a homogeneous deformation occurring inside the material. Then there is localized deformation because now the particles are in contact. There are some interparticular deformations that occurring, and after that, there will be a bulk compression of the material taking place. So this is the sequence of the events that goes in the compaction process. Now we have one question that is related to the critical speed of your milling. This is actually in context to the process of mixers also, where you see we have seen there are two cases where we have seen that we have a ball mill, and this ball mill can be utilized for milling purposes. That means we have to fabricate the mills. We have to fabricate the powders. So we'll go for milling process where we'll have a ball mill. It will have some balls inside it, and these balls will rise to some height, and then they will be falling down at the impact. They will impact at somewhere, and there will be some crushing occurring. This is one of the process which is ball milling. There is also one concept where we are saying that de-agglomeration of the material has to be done, right? As I said, we have particles such as red mud that has a natural agglomeration taking place. So whenever you start with the red mud powder, say for example, and you will always go for milling it or mixing it. You will go for sending it to a mixer for de-agglomeration because you want the particles to de-agglomerate. You can use a heating method, you can use other method, but one of the method is also for like you can use a milling process or you can use mixers for that. So both of these problems utilize the same concept of critical speed. So you have to run them at a certain speed so that they can do the process efficiently, that they mill the material. Basically here you have to mill it, you have to fragment it into pieces, while here you just have to de-agglomerate it. You just have to remove the bonds between the particles. So for de-agglomeration also such mills are being used. So the concept is same in both cases. They will let you to find the critical speed of the mill or the critical speed of the mixer. So based on that, you can identify the like what is based on your diameter of your mills and diameter of the like grinding medias. You can identify the critical speed of the mill. So based on that, we'll do one of these questions. The question says that you have to calculate the operational speed of a ball mill from the given data. So you are given a diameter of the mill is 800 mm. So this is your mill dia, and the diameter of your ball is 60 mm. So if critical speed is 40% less than the operational speed, always remember when you go for a ball mill, there are certain points to remember. One point is that the ball mill does not run with the 100% loading capacity, right? It is always 30 to 40% loading. Maximum 30 to 40% loading happens. That means rest of the material, the rest of the space inside the mill is free. Also, this out of the 30 to 40%, there is the charge that is being used. The material that you are milling, the powder, the feed, you can say, the feed material, and your balls. That are the charging materials, and it is only 30 to 40% of the capacity of the mill, because you need a free space inside the mill for the powders to follow a certain trajectory, and so that there will be milling or deagglomeration, whichever you want. So this is one of the important factor. Another factor is that the critical speed of the ball mill, that the ball mill does not operate at their critical speed. It always operates at less than the critical speed. Say for example, if I write this is the operational speed and not, it will always be less than the critical speed. Some run it at 60%, 70%, or say 30% of capacity. So you can say that it is always less than the critical speed of the ball mill when you are operating a mill. So this is another point, and also the efficiencies of these mills is very less. They are not very efficient because obviously you are trying to, if you are taking for example 1 grams of your feed, you have to take 10 grams of your balls. So you are basically uh, you are basically using the energy for rolling or milling 11 grams, but that out of those 11 grams only 1 gram of the material is being actually milled. So that means you are giving a large amount of energy for the milling, but only small amount of those energy is actually used. So it is very less efficient. It is not very efficient, but it is used largely in the industrial processes. So efficiency of the processes is very low. So these are some general features of this ball mill. Now, based on the question, we have to calculate the operational speed. Before we calculate the operational speed, we have to calculate the critical speed. We know that the critical speed of the ball mill is given by 1 by 2 pi under root of g, which is the acceleration due to gravity, divided by r, capital R minus small r. So this is the radius of your mill, ball mill, and a small r is the like radius of your balls that are being rotated in this mill, right? So based on the equation, you can calculate the critical speed. So first you can calculate the critical speed. You can take 2 minutes and then you can calculate. This is 9.8 divided by the radius of your ball mill. Remember, all the units have to be given in standard SI units. So this is 800 mm. So this will be 0.8 meters, and this is 60, so this will be 0.06 meters. So you can put the data here, 0.8 minus 0.06, because we are given this is a diameter, so we can multiply it by 2. We can calculate it. We can calculate the critical speed of the ball mill. Can somebody calculate? If you can calculate, what is the answer for this? Can you calculate the critical speed? Can you calculate the answer? I think the answer is 0. I think it is 0.82 revolutions per second, right? But what we asked is operational speed. We know that the critical speed, the n critical, is less than the operational by 40%. So we can say n critical by n operational divided by the n critical is equal to 14%, that is 40 by 100, right? That is equal to 0.4. We can say that the n critical by n operational is equal to 0.4 plus 1. We can say it is 1.4. So we can say that n operational, n critical by n operational, it is equal to 1.4. The factor is 1.4. So you can calculate the n operational, that would be 0.82 by 1.4. So this will give you the operational speed. Is it clear? Is there any question? Any question? Any questions?
No, ma'am. Looks fine.
Okay, fine.
Just a second. Hold on. That NC minus NO divided by NO.
Yes,
Uh, that reference at the denominator NO is taken. Why not NC at the
because
denominator?
the critical speed is less than the we are just taking, we're just trying to see what is the critical speed is 40 times less than the operation speed. If it would have been the operation speed is less than, then we have taken because the reference is the critical speed. The critical speed is 40% less than the operational speed. That is why I have taken NC. There are any other method by which you can find the relationship between NC or NO, that would be fine using this data because it's 40% less, that means it is 1.4 times more. So
So denominator is NO or NC, ma'am?
it is NO.
So in this context, you're saying the reference was operational speed. That's why you were taken at
Yes, yes.
NO at the.
Yes, you can do any other method because this is simple mathematics. If you can find the critical speed and the operational speed, you just have this is data for which you have to find a relationship between the two, right? But it is 40% less. How will you find that? So any other method you have, better any method, so that you can also use. Okay, then we have another question. So this is a simple question based on same mill diameter. So we know the find the mill diameter when the critical speed of the mill is 20 and the diameter of the balls is 10. So you are giving the NC, the critical speed is given, that is 20. You have been given the diameter of the balls, that is P. We say that it is 10. Okay. So you can utilize one of the uh, for this you can directly utilize one of the equation that says this is mostly useful when you are going for gate exams and all those where we have taught that the critical speed is related to 42.3, that you are just you have simplified the equation and now it is 42.3 under root of the diameter of your mill minus the diameter of your or radius of your this ball. So you can write it small d. So this is the relationship between the critical speed and the diameter. Simplified equation when you just have to calculate uh, the difference between the diameter and critical speed. So this is very important when you are for a competitive exams. You remember the equation and then you can just plug in the diameter values. So you have to find the diameter of the mill. Okay, so you have to find this capital D. So you are given the mill critical speed of the mill. So you can say you can go like this. That says under root of D minus D is equal to 42.3 divided by 20. Okay, and then we have capital D that will be equal to same 42.3 divided by 20 square plus small d. So just have to calculate. So you know the diameter of the balls, it is 10. So you just have to plug in the values. 42.3 by 20 square plus 10. And that will give you the diameter of the mill. And that will be in the same units as is there. It is the diameter of your ball. So can you calculate what is the answer for this? This is our last question for the day, and you can calculate it and tell me what is the answer. This is very useful in remembering the formula for any competitive examinations because it is a simplified equation where they have given only the relationship between your diameter and critical speed. If you have solved it, you can tell me the answer. Can you tell me the answer?
Is it 10.2, ma'am? What?
I think you just have to, this is 10, so it will be plus something. So what is the value? This will be 42.3 divided by 20. So you just have to square root that 2.115. That will be 4.47. 10 plus 4.47. So that will be 14.47. 14.47 RPM if we consider all the values that given in RPM. So RPM. Sorry, not RPM because we are time from 9 to 7. The 14.4 meters. Is it clear? Is it clear?
Yeah, that
Uh,
20 unit is RPM revolutions per second. It can be anything.
yeah, it can be anything. So I've just considered that these are in the standard units, so that is why I just put the meters value. That is why whatever the value of the diameter was here, you have to just put it down. This is 20, considering this 20 RPM, RPS.
Oh, okay.
We also have one question that says that density of the, this is based on theoretical density. This is the last question for today. So based on your theoretical densities, you have to calculate the theoretical density for a powder that is mixed with its, so for example, some of the material. So I have written a cellulose material. So I just want to calculate the theoretical density. So we have two formulas for theoretical density. One is based on your rule of mixtures, and one of the problem is based on your based on your weighted averages. So based on your weights and based on your density. So we'll try to find the theoretical density by both methods, right? So first you are given the density of your copper, and it is mixed with 2 weight percentage cellulose, and the density of the cellulose is given. Okay, this is a hypothetical example. So we are saying calculate the theoretical density. So first, how will we calculate the theoretical density? Based on rule of mixtures. We will say weighted fraction of A multiplied by the density of the A plus what is the weighted fraction of B and what is the density of B, right? So we will multiply the density. So we have weighted fraction of A for copper here because the 2% is cellulose, considering the rest of it is copper. So that would be 0.98 weight fraction copper. So then we have multiplied by the density. What is the density of your copper? So that is 8.9, right? And we now have the weight fraction of your cellulose, which is the particle B. So the weight fraction of the cellulose would be 0.02, correct? And then we have the density of the cellulose, that is 1.5. So this is your rule of based on your rule of mixtures. What is the density of your material, the theoretical density? So you just have to multiply the weight fraction with its density, weight fraction and its density. So you can tell me what is the answer here. Can you tell me what is the answer in grams per kg?
8.70.
Okay, so it is 8.7. We have also another method of finding the densities that is based on the theoretical density. This is a formula that says you can find the density by saying what is the weight of your powder A plus what is the weight of your powder B divided by 1 by divided by the weight of your A divided by the density of A plus what is your weight of B divided by the density of B. So this is another formula for calculating the theoretical density. So because we are considering that it is like 2% cellulose added to copper, so we can say weight of A plus weight of B is, say for example, 1, right? It is total to 100%, so 1. Then we have weight of A, that will be copper. So the weight of it copper, we can say for example out of 1 it was 0.98 grams or 0.98, right? And density of copper is 8.9 plus the weight of B, that is 0.02 divided by 1.5. So can you tell me what is the density now? There are two methods to find the density, this and this. Can you tell me what is the answer?
I think 8.1, ma'am.
Okay, so it is 8.1, 8.1 grams per cc. So you will see that there is slight difference in the densities. This is 8.75, this is 8.1. So there will be always some difference in the values of the density if you calculate using this or using this method. But both methods are correct. So you can calculate the densities based on your theoretical density when you have a mixture of your powders, right? There could be some another powder also, for mixture of three powders or mixture of some other powder. So that is it. Also, you have to remember because when you are mixing the powder, the density of the material obviously because for 100% copper it is 8.9, but because you are adding some other material which is having a lower density, the overall density will decrease, right? So it is always a mixture of the proportion in which they are being mixed. Because it was mixed only 2%, so there was a slight decrease in density. But it would have been added in a larger proportion, the density will be largely decreased. So you will be compromising on the density. The density of your compact will not be same as the density of your pure material, right? Because you have added certain additives. There could be another powder that you are adding. There could be another lubricant binder or any other material that you could be adding to the powder. But the density of the material will change. It will change based on what is the density of the material that you are adding and in what fraction you are trying to add in. So you have to remember that you might be compromising the density if you are adding, say for example, some other material in a larger proportion. So you will be compromising the density. So you have to modulate how much it is to be added and in what weight fraction, like what is the weight fraction of addition and what is the density of that material. So this will help you to calculate the theoretical density for a compact or for a material that you are mixed. So I think this is for today. If there is any question you can ask.
First rule is called rule of mixture, madam.
Yes, yes.
So second one is called as
I don't think there is any name for that.
there is no specific name for that.
No,
It's,
I don't think there is any name. I don't think
yeah. Now the thing is, which one should we use for our
so.
formula?
Well, mostly what we do, we whenever even if we have any mixing substances, whenever we are trying to mix, we usually go for rule of mixing. Even if it is for liquids, even for example, here it was a weighted average of a material which is a powder, like by which is a solid material. But even if you have a liquid, if you have two liquids and you are mixing them, and then you want to find the density of the liquid that is formed after mixing the two, we can also find the density using the same rule. So this is a very general rule for mixing. If you are mixing two or three species, then you can use this formula in any way possible. You are multiplying the weight and density to find the density of the theoretical density, right? Similarly, you can find some other factor. If it is not density, if it is volume fraction, if it is some other parameter. So the this is a very general kind of a description for finding a root of mixing. If you do not know any formula, then this is the best way to do. For a basics, it is best. But also, this is not the wrong method because the difference in the densities is not that significant. So you can use either of the two. Rule of mixing is a general rule. It is used for all. It is just not limited to powders and their theoretical density. It can be extended to liquids. It can be utilized for determining any other parameter other than the theoretical density, whether it is volume, whether it is weighted average, or if it is anything else. So you can calculate using that. So both of these methods are right. So there is no problem in utilizing using any of them.
And in this only main ingredients, we are not considering lubricant, we are not considering binder.
Why it depends when you are trying to go for forming a powder and you want to calculate the theoretical density, then you should take all those into considerations, right? But for example, if you are using a binder that you are using in 0.1% or 1%. So there will be not significant difference, right? Based on what kind of a proportion you are using. But if you are using two powders, you are using 50% powder A, 50% powder B to form an alloy, then there is a significant difference that is going to be in density. So in mixing of your two metallic balls or metallic powders to form an alloy, that would have a significant difference in the density. But if you are mixing small lubricants, because that is very less percentage, 0.1 percentage, less than 1 percentage, 1 plus 2 percentage. So if you even if you see it was 8.9 to 8.75, right? So there was a difference in density, but obviously it will not affect because the fraction of the material that was added is very low, and always the density of your lubricants and all of these materials would be very less because they are organic molecules. So their density is always low. So, but when you are alloying it, when you are mixing the two powders of same like of metallic species, then there is a significant difference. So in those that will be crucial to find the theoretical density for your composite material that you are forming. So based on what is your requirement, you can calculate the theoretical densities.
My point was, ma'am, like WA, WB are the two, like copper and something zinc I have added. Uh, but in this, along with WA, WE, should I consider the binder used like WC
Yes, you can see
and
if for example if you are using any binder and you are using it in some proportion, you can use it. If it you can add it, you can just add one more distractor here, so that would be WC plus density of the C. So you can just add that WC plus
yeah, but
density of C.
that will be true only during the green stage.
Yes, during
But
the
after
that's correct.
sintering, everything will go. So
Yes.
that time, like,
Then you
should
cannot then you should not consider it. Right,
so
right,
if I'm
right.
going sintering, then I should not
And
consider
then you
only
should
the
consider only the major components that are part of the powders. Yes.
okay. Yeah,
Okay. Okay, I think that is all for today.
thank you, ma'am.
Thank you. Thank you.